Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best condition of your health. So today in connection with the lectures on the course of organic reaction mechanism, we will discuss about the aromatization process. So in this lecture we will consider that which common oxidizing agents are used for elimination of hydrogen resulting in formation of aromatic compounds. So the key concepts which we will discuss here are the oxidation and oxidizing agent, and what are the reactions that involve elimination of hydrogen, and how we can carry out the aromatization reaction. Right, so firstly, oxidation and oxidizing agent. So first we will define what we mean by an oxidizing agent. So oxidizing agent are also known as oxidants. So any species which gains electron and is reduced in a chemical reaction, right? So this is called the oxidizing agent or the oxidant, right? So in short, we may say that oxidizing agent is actually the electron acceptor. So it normally the oxidizing agent is the one which is in the highest possible oxidation state, because when it's in a highest possible oxidation state, it will gain electron easily, right? So the common oxidizing agents which are used are hydrogen peroxide, ozone, oxygen, potassium nitrate, nitric acid. All of these are oxidizing agents because all of these are in higher oxidation state. So if a species is in lower oxidation state, it cannot accept electrons, right? So for any species, for any reagent to be oxidizing agent, it must have higher oxidation state, means it must be a good acceptor of electrons, right? So along with these, all of the halogens, these are oxidizing agent because they need just one electron to complete their outermost shell, so they can easily accept an electron, right? So therefore all of these are also oxidizing agents. Now, next is the oxidation process, chemical reaction that involves or that result in loss of electron in a compound which is being oxidized, right? So a process, a reaction in which an organic compound is oxidized, or process in which an organic compound loses electrons, this reaction is called oxidation, right? So depending on the type of bond change involved, oxidation reactions are classified as reactions which involve elimination of hydrogen, reactions that involve cleavage of carbon-carbon bond, reactions which involve replacement of hydrogen by oxygen, or reactions in which oxygen is added to the substrate, and lastly oxidative coupling. So our concern today is reactions that involve elimination of hydrogen. So there are different types of oxidation reactions which involve elimination of hydrogen. So among these is the aromatization of six-membered ring, which is the topic of our today's lecture. Then dehydrogenation reactions which yield carbon-carbon double bonds, dehydrogenations of alcohols to result in formation of aldehyde and ketones, oxidation of phenols and aromatic amines which will result in formation of quinols, then dehydrogenation of amines to form nitriles, oxidation of hydrazine, hydrazone, and hydroxyl amines, right? So we will discuss them all one by one, but today's lecture we will only concern about the aromatization of six-membered ring, right? So let's consider about the aromatization of six-membered ring. Alright, so suppose we have a six-membered ring that's a cyclohexane, and we are going to convert it to aromatic ring that's benzene. So normally the reaction takes place in presence of catalysts which are used for hydrogenation, and the catalysts which are normally used for hydrogenation are also useful for aromatization. So these catalysts involve platinum, palladium, sulfur, selenium, etc. So it has been generally observed that when we are carrying out the aromatization reaction, if our substrate already has a double bond, then activation barrier or the activation energy in the formation of aromatic compound decreases. So if you have a cyclohexane or cyclohexene or cyclohexadiene, so cyclohexadiene will react very fastly. Why? Because as the degree of unsaturation increases, the aromatization becomes easier. So अगर आपकी substrate के अंदर कोई भी double bond नहीं होगा, उसको aromatize करना मुश्किल है. लेकिन अगर आपकी substrate में एक double bond हो या दो double bonds हो, then उस सूरत में आपकी substrate को aromatize करना आसान हो जाता है. Because जैसे जैसे number of double bond increase होता है, वैसे वैसे जो activation barrier होता है या जो activation energy होती है, that decreases, right? So in laboratory level, when benzene derivatives are prepared, so they are either prepared by dehydrogenation of cyclohexane or cyclohexene or cyclohexadienes and their respective derivatives, right? So you may either use cyclohexane or substituted cyclohexanes. You may use cyclohexanes or substituted cyclohexanes. Similarly, you may use cyclohexadiene or substituted cyclohexadiene, right? So in order to carry out the aromatization by using platinum or palladium, so we have to maintain high temperature, approximately 300 degrees C with these catalysts. And the reaction works well in case if the palladium or platinum catalysts are used as finely powdered. So either you have to use the catalyst as finely powdered state or they have to be deposited on activated charcoal. So why we use powdered catalyst or the catalyst deposited on activated charcoal? Because in this case the surface area has enhanced, so with greater surface area the reactions work well. So in case if you use a solid catalyst, then surface area is lower. So because of lower surface area, the reaction does not work well. Right? So the reaction is driven towards aromatization or dehydrogenation because of removal of hydrogen from the equilibrium. Right? So as soon as the hydrogen is formed, it should be removed. So when the hydrogen is removed, the equilibrium reaction is shifted towards the right side. So the reaction also works well if you have a hydrogen acceptor present in the reaction, right? So in the reaction, suppose we have a cyclohexene and the cyclohexene is being converted into benzene. At the same time, we have two hydrogen molecules that are eliminated. So the reaction is reversible reaction. But in case if you have to increase the yield, what we do that we trap this hydrogen out of the reaction mixture. So you have to keep the Le-Chatelier principle in mind here. So if you can remove this hydrogen from the reaction mixture, right, so you can shift the equilibrium on the right side. So how you can remove the hydrogen? By making use of hydrogen acceptor. So malic acid is a very good hydrogen acceptor. So hydrogen gets added to the malic acid because malic acid has a double bond, right? So as soon as hydrogen is produced, it gets added on the malic acid. So malic acid is a hydrogen receptor, so equilibrium shifted on the right side, right? Also the equilibrium is shifted in favor of the product because large number of molecules are produced, because we have one reactant, and suppose in that specific case when we are using cyclohexene, so we get a benzene molecule plus 2 molecules of hydrogen, so we get 3 molecules of product and 1 molecule of reactant. So on the right side, since number of molecules is increasing, it means that entropy is increasing. So any reaction that involves increase in entropy is always favored. So the forward reaction is also favored because of increase in entropy. Alright, so previously as we mentioned that if a 6-membered ring already has a double bond or it has a 2 double bond, then aromatization occurs very readily, right? So also aromatization is very rapid when a 6-membered ring is fused with an aromatic ring. Right? You can predict why it's so, because if a system is already aromatic or if a system is attached to an aromatic ring, then it has the tendency to cause an extension in conjugation, right? So if a system has already a double bond or 2 double bond, or if a 6-membered ring is attached to an aromatic ring, then because of decreasing the energy barrier, because of tendency towards aromatization, the aromatization becomes very rapid. Okay, let's just consider these 3 systems and just compare the temperatures. So if we have no double bond in the 6-membered ring, so 350 degrees C temperature is required to get the cyclohexane converted into benzene. But if you have a double bond already existing in the system, then temperature of 300 degrees is required. But if you have two double bonds in the system, just see that it's about 90-degree temperature that's required to convert this substrate into product, right? So it's generally believed and generally observed that last double bond in the 6-member ring is formed under most milder conditions, because it's very easy to generate a double bond because the energy barrier has reduced to very lower amount. Right, suppose we have a 6-member ring and we have to carry out the aromatization, and suppose that it has substituents attached to it. So we are here to determine what will be the fate of these substituents. So what will be the result of these reactions. So suppose that consider we have a system which is substituted and we have to carry out aromatization. So aromatization is not prevented by presence of any substituent on the ring, right? So even you have two alkyl groups attached to the same carbon, which are known as geminal alkyl. So suppose this example. So here we have two methyl groups which are attached to this carbon of cyclohexane. So apparently it becomes it appears to be different, that this will not be aromatized. But when we carry out the reaction under the same conditions, 400 to 500 degrees C, then in that case one of the methyl has been eliminated. So if you have a geminal substitution pattern on the 6-member ring, then one of the substituent either is lost or it undergoes migration, right? However, when you have a geminal substitution present on the 6-member ring, then you have to use more drastic conditions. We have to use more harsh conditions. So if you use low temperature conditions, under these conditions aromatization will not take place. So similarly, if we have a hydroxyl or carboxyl group present on the 6-member ring, right, then what will happen, that initially the ring will cyclize and form a carboxylic acid with benzene, right? So this benzene will form carboxylic acid, will be retained, and then you may remove this carboxylic acid by simply reacting with soda lime, right? So sodium lime is basically sodium hydroxide with calcium oxide. So if you have to remove a carboxylic acid group from any functionality, soda lime is the best reagent of choice. So you can simply convert this benzoic acid into benzene by elimination of carbon dioxide, right? So if you have a cyclic ketone, but conditions, it should be 6-membered ring. So if you have a 6-membered ring and there is a ketone in the ring, then such ketones are converted into phenol. You cannot form benzene from it, right? So 6-membered ring with ketonic group inside, they result in formation of phenols. And if you have a 7-membered ring, then under same reaction conditions of platinum or palladium or heating at high temperatures, then 7-membered rings are isomerized to form 6-membered aromatic ring, and the 7th carbon becomes the substituent. For example, if you are using cycloheptane, then in that case we will form a benzene ring with a methyl group as a substituent, right? So in brief, we can say that when we have to carry out the aromatization of a 6-membered ring, it doesn't matter whatever substituent are present. So you can just imagine that if we have a dialkyl substituent which are at geminal position, means if you have a geminal substitution, then in that case one of the group may either be eliminated or it may migrate to some other position, or it can be limited all. If you have a hydroxyl group or carboxyl group, that will be retained, and if you don't want them there, then you can simply remove that. For example, if you have a carboxylic acid group, then in that case it will be lost from the ring. For that purpose you have to use soda lime. If you have cyclic ketones, then cyclic ketones are converted into phenols under this condition. And if you have a 6-membered ring, then the 6-membered ring, if you have a 7-membered ring, then 7-membered ring will isomerize to form a 6-membered aromatic ring. So now we consider that suppose we are to carry out the dehydrogenation of cyclohexane 6-membered ring, and for that, as I mentioned, that you have to use catalysts which are used for hydrogenation, right? So these catalysts which are used normally for hydrogenation, such as platinum, palladium and nickel, they are also very good for causing dehydrogenation, right? So these are very effective for causing the aromatization as well. So it has been found that the cyclohexene is the intermediate in this reaction. Cyclohexene has been detected as, cyclohexadiene has been detected as an intermediate in this conversion of cyclohexane to benzene. So we can predict that actually the reaction mechanism involves step-by-step generation of a double bond. So when you start with cyclohexane, the first step is generation of a carbon-carbon double bond, and in the next step the cyclohexene is converted into cyclohexadiene. So cyclohexadiene has been confirmed to be intermediate in this reaction. So in this specific case we have platinum as a catalyst, and we are using temperature of 350 degrees C. So this is the overall temperature of the reaction mixture, not for that specific reaction. Right. So in case suppose that you are not preferring this platinum, palladium or nickel for a certain reason, you can also use sulfur and selenium as catalyst. So sulfur and selenium, they are mild oxidizing agents, so they work slowly, they require lower temperature as compared to the reaction for platinum, palladium and nickel, right? So the reactions works in such a way that because the hydrogen is removed by binding of these hydrogen atoms with sulfur or with selenium. So the reactions involve formation of hydrogen sulfide or selenic acid. So H2S or H2SE are formed in this reaction. So we get hydrogen sulfide or selenium sulfide, or selenic acid as a reaction, as the side product of this reaction, right? So because of development of hydrogen sulfide or selenic acid in this reaction, so because of their foul smell, this reaction is of little preparative value. Although reaction is very simple, reaction is very easy and occurs in mild condition, you don't have to give high temperature for this reaction, but because of this foul smell of hydrogen sulfide or selenic acid, so this reaction is not preferred, right? So although otherwise selenium and sulfur, these both can be used for generation of aromatic ring, or these are very useful for generation of or for creation of aromatization. Right, so there is an example in which you can see that how selenium can be used for aromatization. So this is the structure of cholesterol. Right, and you may be surprised that this reaction was actually used for confirmation of structure of this cholesterol. Right, so cholesterol, when treated with selenium, right, that causes the aromatization of ring A, ring B and ring C. So as you know that the steroids have 4-ring system. So first is 6-membered ring, then 6-membered ring, then 6-membered ring, and then 5-membered ring, right? So this one ring with normally a hydroxyl group at this position, which is carbon number 3. So we start carbon numbering here 1, 2 and 3. So this hydroxyl carbon number 3, this is characteristic of normally the estrogens. So this ring, this 6-membered ring, this is known as the A ring of steroid. So this ring is called the B ring of steroid, this is the C ring, and this 5-membered ring is the D ring. So steroids have 6-6-6-5 pattern, right? So in order to confirm whether there is ring A, which is 6-membered ring, or not, so this reaction is performed. So for that purpose, selenium was used and temperature of 350 degrees C was maintained. So at 350 degrees C, selenium caused aromatization of ring A, ring B and ring C. It's also important to note that the aromatization of ring B took place first, and you may see for the reason why it took place first, because there's already a bond, a double bond, which is present between the ring A and ring B. So because of presence of this double bond, then the energy barrier for further aromatization of B ring was reduced. and once the pairing was aromatized, then the aromatization of ring A and ring C took place very rapidly. Alright, so this is the application of how we can use the sulfur and selenium as dehydrogenation catalysts. So normally you may say that the catalysts which are used for dehydrogenation are also used for dehydrogenation as well. Okay. So now we are considering the use of quinones for aromatization of 6-membered ring. Right, in this reaction, the quinone is oxidizing agent. So what I mean by oxidizing agent, it means that this quinone will accept an electron. Right, so here you can see how it can accept an electron, because the quinone is highly conjugated system. Also, this is highly electronically deficient, so it can easily accept an electron, and once the electron is been accepted, that will be resonance stabilized. Right, so quinones are very good oxidizing agents. It can accept electron very readily. Since it can accept electron very readily, it means quinones can be easily reduced. It means it can easily oxidize our molecule. Right, so quinones, actually what happens that quinones accept this hydrogen in the form of hydride. Right, so this molecule, which is cyclohexadiene, that gives up a hydrogen in the form of hydride. So this hydride is transferred to the quinone system, and the quinone is reduced to quinol. Right, so this is hydroquinone. Right, so this quinone is reduced to hydroquinone. Right, and this cyclohexadiene, that becomes a carbocation with positive charge on this carbon. Right, so what happens that in order to neutralize this positive charge, the proton from the carbon, which is adjacent to this carbocation, so this proton that leaves, and why it leaves, because this oxygen, which is negatively charged, so this oxygen of the hydroquinone, it picks up this proton. Right, so when it picks up this proton, so this proton gives its electron, and a carbon-carbon double bond is formed between carbon and this carbocation. So here we get a benzene ring, and this is the hydroquinone that has been reduced. See, it happens. So we have a quinone, which is a conjugated system, and why we are using quinone, because they are highly electronically deficient. Right, so since it's electronically deficient, it can easily accept an electron. Right, so what happens that this hydrogen is transferred from our molecule to the quinone. Right, so this hydrogen is transferred in the form of hydride. Right, so hydride is transferred from the molecule to the quinone. So quinone is being converted into hydroquinone. Right, that's a reduced form of quinone. Right, so we have a positive charge on this carbon. Right, what happens that this negatively charged oxygen will pick up the other proton, and this proton will then leave with giving its electron between this carbon and this carbocation. So here it's important to note that the proton which the hydrogen is transferred to quinone is hydride, and the proton which is picked up by this hydroquinone, that's a proton. So hydrogen can exist in the form of molecular hydrogen, which is normally referred to as H2. Hydrogen can exist in the form of H positive, which is normally known as proton, and hydrogen can also exist as H negative. So H negative means hydride. Right, so firstly, the proton which was the hydrogen which was transferred was hydride, means H negative. This was electronically rich hydrogen. Right, so the loss of electronically rich hydrogen leads to formation of carbocation here, and the next hydrogen that was lost as a proton, because that was electronically deficient. So this hydrogen gave up its electrons for bonding with this hydroquinone. So in this way we can get a benzene ring and a hydroquinone ring there. So instead of using simple quinones, we can make use of more electronically deficient quinones as well. So the more deficient a quinone is, the faster the reaction works. You may see the reason why is that so, because the quinones, if they are electronically rich, they will not be able to accept electron, right? So we are using this quinone as a oxidizing agent. So oxidizing agent is better if it is electronically deficient, because it has to pick up electron, right? So this quinone, this is known as DDQ, stands for 2,3-dichloro-5,6-dicyano-1,4-benzoquinone, right? So because of presence of these nitrile groups and these chloro groups, right? So all of these four groups are highly electron withdrawing, right? Because of this electron withdrawing nature of these groups, so this quinone is highly electronically deficient, right? So since it's electronically deficient, it works well. So first step will be just the transfer of hydrogen from our molecule to the quinone. So first hydrogen will be transferred in the form of hydride. So that will be converted into hydroquinone, and the hydroquinone will pick up the next hydrogen, and the next hydrogen which this quinone will pick up will be in the form of proton, right? So we'll get a benzene ring here. So substituents will remain the same. There will be no effect on substituents in this specific case, and we will get the hydroquinone from that purpose. So if you can see that the yield of this reaction is 100%, right? So also compare the temperature. So in case of other conventional methods, we have to maintain higher temperature like 350, 500 degrees C, but this DDQ, it works only at 20 degrees C, and we have to wait for 12 hours. So the reaction time is 12 hours for this reaction. So in 12 hours, we can get our product in 100% yield. Now another alternate is chloranil. Chloranil is this one. So chloranil is basically 2,3,5,6, right? So you can say 2,3,5,6,1,4-benzoquinone, right? This commercial name is chloranil. So chloranil is not that much electronically deficient as DDQ. So since that's not much electronically deficient as DDQ, so you may predict that its reactions will not be much fast. So you can compare the yield. So you have to wait for 24 hours, and the yield is 63%, and the temperature you have to give for this reaction is 120 degrees C, right? So after 120 degrees C and waiting for 24 hours, which is almost double time in comparison with the DDQ, so we get the product with only 63% yield. So mechanism will be same. So firstly, we will have a transfer of hydride from our molecule to this chloranil, and will form hydroquinone, and then hydroquinone will pick up a hydrogen in the form of proton from the molecule. So we'll get a hydroquinone, and we will get the product which is aromatized here, and the yield is 63%. Okay, so if we are going to carry out the synthesis of substituted aromatic compound, so if you are going to synthesize about toluene, that's which is called methylbenzene, or you are interested in the preparation of xylene, right? So they can be easily synthesized from hydrocarbons of 6 to 8 gasoline fraction. 6 or 8 gasoline fraction in gasoline fraction that has 6 carbons or 7 carbons or 8 carbons, right? So gasoline fraction that has 6 to 8 number of carbon atoms. So such hydrocarbons, they are obtained from petroleum refining, right? So what we do is that we get these hydrocarbons and first we cyclize them, right? So conversion of the straight chain hydrocarbons into cyclic hydrocarbons, this is called catalytic reforming. And the interesting thing about catalytic reforming is that if you have 6-membered ring, that will cyclize to form 6-membered ring. So if you have 6 carbon straight hydrocarbon chain, then that will form 6-membered ring. Even if you have a 7-membered straight chain of hydrocarbon, that will again cyclize to form a 6-membered ring with a methyl group as a substituent. And if you have 8-member straight chain, then it will form a 6-membered ring with 2 substituents, the 2-methyl as a substituent, right? So conversion of the straight chain 6-membered hydrocarbon chain or higher number of carbon chain into 6-membered ring, this process is called catalytic reforming, राइट। तो अगर आपका स्ट्रेट चेन हाइड्रोकार्बन हैं जिनमें 6 कार्बन हैं या 7 कार्बन है या 8 कार्बन है, इन स्ट्रेट चेन हाइड्रोकार्बन्स को जब आप 6 मेंबर रिंग में साइक्लिक रिंग में कन्वर्ट करते हैं, दिस प्रोसेस कॉल्ड catalytic reforming. And for catalytic reforming, the catalysts which are normally used are alumina. You have to make use of alumina for this reaction, right? So catalytic reforming, so next process क्या होगा, catalytic reforming के बाद हम इसको aromatize करेंगे, right? So in this process जो gaseous हमारे पास hydrocarbons होते हैं, they are dehydrogenated at aromatic compounds at temperature 450 to 550, and we have to use the pressure of 1000 to 5000 kilopascal. And normally the catalysts we use are platinum on aluminum oxide, right? So platinum on aluminum oxide, we are not using platinum alone because platinum alone is very expensive. So what we do is that we disperse this platinum, which is used in the form of powder, on aluminum oxide, right? So we just mix the platinum powder with aluminum oxide. So in this way we have to use minimum amount of catalyst. Also the surface area is very huge, right? So अगर आप platinum alone यूज़ करते हैं, अकेला platinum यूज़ करते हैं pure form में, then उस सूरत में क्या होगा कि platinum हमें बहुत expensive पड़ता है, that's very expensive, और आपको ज़्यादा इस्तेमाल करना पड़ेगा. तो हम क्या करते हैं, प्लेटिनियम को लेके उसको पाउडर कर लेते हैं, और पाउडर करने के बाद उसको एल्यूमिनियम ऑक्साइड के साथ मिक्स कर देते हैं. तो जब आप एल्यूमिनियम ऑक्साइड और प्लेटिनियम को मिक्सचर लेंगे तो आपको कैटलिस्ट भी थोड़ा इस्तेमाल करना पड़ेगा. इवन इफ़ आपने ज़्यादा भी लिया होगा तो इसमें एल्यूमिनियम ऑक्साइड ज़्यादा होगा, प्लेटिनियम कम होएगा. तो दैट बिकम्स अ चीपर मेथड. ऑल्सो चूँकि आपने दोनों को पाउडर फॉर्म में लिया हुआ है तो सरफेस एरिया ज़्यादा होएगा, राइट. तो इफ़ यू हैव टू कन्वर्ट द सब्स्टिट्यूटेड साइक्लोहेक्सेन्स into benzene ring, the most preferred way is to make use of platinum over alumina. Alumina is also called aluminum oxide, and you have to maintain high temperature of 450 to 550 degrees C, and you have to maintain a high hydrogen pressure of 1000 to 5000 kilopascal. So in this method, अगर आपके पास starting material है 1,2-dimethyl cyclohexane, then you ore those ions, right? ओके. सो अगर आपने लास्ट स्लाइड थोड़ी सी गौर से देखी हो, आपने देखा कि हमने जो है वो एरोमेटाइजेशन की साइक्लोहेक्सेन की. तो एरोमेटाइजेशन के दौरान में हाइड्रोजन गैस इवॉल्व होती है, ऑल्दो हाइड्रोजन गैस इवॉल्व होती है लेकिन फिर भी हमने हाइड्रोजन प्रेशर ही रखा. सो व्हाई इज़ दैट नेसेसरी? बिकॉज हाइड्रोजन ऑल्दो इट्स अ प्रोडक्ट रीफॉर्मिंग, कैटालिटिक रीफॉर्मिंग में भी हाइड्रोजन प्रोड्यूस होती है, लेकिन हमें एक्सेस ऑफ हाइड्रोजन चाहिए. बिकॉज अगर आप एक्सेस ऑफ हाइड्रोजन इस्तेमाल नहीं करेंगे दैन आपका कैटलिस्ट डिस्ट्रॉय हो जाता है. Right, you have to ensure that hydrogen is in excess, because अगर हाइड्रोजन एक्सेस में रहेगी तो आपका कैटलिस्ट एक्टिवेट रहेगा, राइट. अगर हाइड्रोजन एक्सेस में नहीं होती तो what happens that the product of this reaction will get absorbed on the catalyst, right. So deposition of our hydrocarbons on the catalyst surface will take place. So आपके जो प्रोडक्ट है, जो हाई मॉलिक्यूलर वेट ऑर्गेनिक कंपाउंड है, वो कैटलिस्ट के ऊपर एब्जॉर्ब हो जाते हैं. सिंस वो कैटलिस्ट के ऊपर एब्जॉर्ब हो जाता है, उसका नुकसान हमें क्या होगा कि आपका प्रोडक्ट भी ज़ाया हो जाएगा और आपका कैटलिस्ट भी डिस्ट्रॉय हो जाएगा, वो डीएक्टिवेट हो जाएगा. सो इन ऑर्डर टू इंश्योर कि कैटलिस्ट भी एक्टिवेट रहता है और आपका प्रोडक्ट भी मैक्सिमम यील्ड में आए, तो हम क्या करते हैं कि हम लोग हाइड्रोजन का एक्सेस में लेते हैं. दैट्स वाई जो प्रीवियस स्लाइड थी उसमें हमने हाइड्रोजन प्रेशर यूज़ किया था, मीन वी यूज एक्सेस ऑफ हाइड्रोजन अबाउट 1000 to 5000 kilopascal. सो यू शुड नो द रीज़न. आपको पता होना चाहिए रीज़न कि हम लोग जो है वो हाइड्रोजन को एक्सेस में क्यों लेते हैं इन दिस रिएक्शन. लेट्स सपोज दैट वी हैव टू सिंथेसाइज phenols by aromatization, right. So phenols and phenol derivatives, they are very important. They are synthetic building block for synthesis of large number of compounds. They are used in the preparation of polymers, they are used in the preparation of dyes, they are used in the preparation of pharmaceuticals. So these phenols are very important for us, right. So we have to synthesize the phenols. So a large number of phenols, a large number of methods are available for the synthesis of phenols, right. But this method of catalytic dehydrogenation is very effective. So what we do is that we just use cyclohexanone or cyclohexenone. So you need to have a 6-member ring with a ketonic group here, our 6-member ring with ketonic group and a double bond here, right? So what we do is that we carry out the catalytic dehydrogenation for that purpose, and the reagent which we'll use in this process is iodine. So इस रिएक्शन में हम आयोडीन इस्तेमाल करेंगे, राइट? तो हम आयोडीन क्यों इस्तेमाल करेंगे? क्योंकि आयोडीन जो है वो ऑक्सीडेटिव एरोमेटाइजेशन को प्रमोट करेगी. सो वेरी स्टार्ट में जब आपने ऑक्सीडाइजिंग एजेंट्स के बारे में देखा था, okay, so in the very start when we discussed about the oxidizing reagents, we mentioned about that halogens are a very good oxidizing agent. So iodine is also a halogen. So why halogens are oxidizing agent? Because they have 7 electrons in the outermost shell, right? So they just require one more electron. उनको सिर्फ एक और electron चाहिए क्या कि अपना electron outermost shell को complete कर लें. So what happens that iodine is a very good acceptor of electron, right? So it's a very good oxidizing agent. So iodine can oxidize this system, and if you have to predict that which of the substrate will be more reactive, so you can easily predict that the substrate with already a double bond will be more reactive than this simple cyclohexene. Right, so in this way, starting from the cyclohexenones or cyclohexenones, we can prepare the phenol. So if this system is substituted, we will get substitution on the phenol ring. So depending on the nature of substituent and position of substituent on these rings, we will get phenols with the substituent in the same position. The position of the substituent on the phenol will not be changed. Right, so that's all about the aromatization reaction. So you have considered different reagents which will be used for carrying out the aromatization. So you have considered the use of platinum, palladium, nickel, which are normally used for carrying out the aromatization reaction, but the limitation of these reactions is that we have to give very high temperatures. Also, it has been observed that if your system 6-member ring already has a double bond, then it becomes easier to convert it into the aromatic system, because the increasing unsaturation promotes the aromatization because of lowering in the activation energy. Also, instead of platinum, palladium or nickel, you may use sulfur or selenium, and they have the advantage that you have to give lower temperatures, but the disadvantage is that they have foul smelling hydrogen sulfide or selenic acid which are produced during the reaction. So because of that foul smell, we don't prefer these reactions. So also we can make use of quinones. So quinones are very effective because they are electronically deficient. So we can make use of quinones. So if a quinone is very highly electronically deficient, the reaction will be much more faster. And if you are using a system, if you are using a quinone which is electronically rich, then reaction will not work well. So the examples of DDQ and chloranil is comparison is very important for this comparison, because DDQ is more electronically deficient and the yield of product is much higher in that case. And lastly, we saw about the use of iodine for aromatization. So in case if you have cyclohexenone or cyclohexenone, you can convert them into phenols by making use of iodine as oxidizing agent. Right? I hope you have understood this lecture well. Thank you.